I'm David Hyatt. Welcome back to Fast Pace. This video program, along with the support materials, will help you pass the ASE engine repair test. If you've not already done so, remove the mini-test labeled engine repair in the answer sheet, stop the tape, and complete the mini-test. When you've completed the test, return to this videotape to review your answers. Engine repair, as with some of the other test topics covered in this series, involves the mastering of many disciplines. Mechanical repair disciplines such as close tolerance measuring techniques, diagnostic test interpretation, and proper machining operations are the areas least understood by technicians for this topic and are the subjects we will emphasize during this program. We'll cover these disciplines by concentrating on the following content areas: general engine diagnosis, cylinder head and valve train diagnosis and repair, engine block diagnosis and repair, and lubrication and cooling system diagnosis and repair. The content areas not covered in this video that will be represented on the engine repair test are covered by the engine repair task sheets and reference sheets. There are a variety of physical tests that can be performed to isolate engine problems. For the exam, you should be familiar with test procedures and test result interpretation for compression tests, vacuum tests, cylinder leakage tests, and cylinder power balance tests. Let's look at some typical questions in this area. A compression test shows all cylinders have low compression. Which of the following is the most likely cause? A, worn valve guides, B, slip timing chain, C, intake manifold leak, D, carbon buildup on pistons. This straight pick type of question has one of those phrases to look out for: most likely. You were to pick the response that best answers the question. Looking at the possibilities, we know that an intake manifold leak would have no bearing on a compression test for several reasons. The most notable being the throttle plates should be blocked open during the test, allowing as much air as possible to fill the cylinder. An intake manifold leak would not alter the air entering the engine in this case. Carbon buildup on the pistons would actually increase compression pressure because the carbon displaces a portion of the combustion chamber volume. And when the air-fuel charge is compressed during the compression stroke, it's compressed into a smaller pocket. When a gas is compressed into a smaller volume, the pressure exerted by the gas increases. Worn valve guides are not a usual source of low compression in all cylinders because it's unlikely that all the guides will wear evenly in an engine. A slip timing chain, on the other hand, will cause uniform low compression in all the cylinders due to altered valve timing. So the correct answer is response B, slip timing chain. A technician is doing a compression test. On one cylinder, compression is low on the first puff, then steadily increases to normal. Technician A says worn piston rings could be the cause. Technician B says a burnt valve could be the cause. Who's right? A only, B only, C, both A and B, D, neither A nor B. This comparative statement tests your ability to interpret the results of a particular diagnostic test. Now, both technicians came to different conclusions from the same test results, so the chances are that they're both not going to be correct. Let's look at the described test and determine if either of the technician's statements are true. Observing the first puff during a compression test can give us a very useful diagnostic information about cylinder seal. Small leaks, such as those found with worn piston rings or light cylinder wall scoring, will not produce high compression on the first compression cycle, but will produce satisfactory results on subsequent cycles due to increased cylinder sealing efficiency caused by increased RPM and hydraulic sealing, overcoming the slight leakage. A low first puff, typically less than 50% of the fourth or fifth puff, can indicate worn rings. Technician A's statement is true. So responses B and D can be eliminated as the correct answer to the question. A burnt valve, as suggested by Technician B, is a large leak in the cylinder seal which will cause low compression on the first compression cycle and low compression on the subsequent compression cycles. In this case, the increased engine speed does not increase sealing efficiency. Technician B's statement is false. Now we can eliminate response C as the correct answer, and that leaves only response A only, as the correct answer to this question. Remember to follow proper procedures when performing a compression test. Bring the engine to normal operating temperature. Stop the engine and disable the ignition system. Remove the air cleaner. Block open the throttle plates. Remove all the spark plugs. Don't forget to read or examine the plugs while out. Plugs can tell you a lot about engine condition. Install the gauge in each cylinder and crank the engine at least 4 revolutions per cylinder to obtain the highest reading. Record the readings in the first puff and final puff and compare to manufacturer specs. Consistent cranking speed is very important to accurate compression testing. If the engine cranks slow, test the battery and the starting systems before continuing the test. Interpreting engine noises is also an important diagnostic procedure. Running noises can be caused by lots of different engine failures, as well as auxiliary component failures. Reaction of failed components to changes in engine operating modes can help us pinpoint the failed components. Auxiliary components such as water pumps, power steering pumps, and alternators can be quickly isolated by belt removal. Isolating internal engine noises involves a few more tricks, such as grounding spark plug wires, loading or unloading the engine, and determining whether the noise is present when the engine is cold, warm, or both. An engine with a manual transmission has a heavy knocking sound at idle. When the clutch pedal is depressed, the noise goes away. What's the most likely cause? A, rod bearing knock. B, excessive piston to cylinder clearance. C, excessive wrist pin clearance. D, worn crankshaft thrust bearing. Familiarity with the noise prints of the responses will help us quickly identify the correct response to this simple choice question. A worn rod bearing knock can be eliminated as the cause of our problem. Rod bearing knocks are most noticeable off idle and increase with engine speed. They become louder when the engine is unloaded and usually disappear when the spark is eliminated from the affected cylinder. Excessive piston to cylinder clearance can also be eliminated. This failure would produce a hollow sound, usually under a load that diminishes as the engine warms up. Piston wrist pins with excessive clearance, as stated in response C, produce a sharp double knock sound which is louder when the engine is cold. In addition, grounding the spark plug of the affected cylinder would eliminate the knock, so this response can also be eliminated. The crankshaft thrust bearing keeps the crankshaft from moving end to end. When this bearing develops wear on the thrust surfaces of the bearing, the crankshaft can move end to end, creating a noise. When the clutch pedal is depressed, it prevents the crankshaft from moving, thus eliminating the knocking noise. The correct answer is D, worn crankshaft thrust bearing. Check your task sheet for other noise prints of failed internal engine components. An engine is running at idle with a vacuum gauge attached. Engine vacuum level is good. However, the needle has a regular downscale fluctuation. Technician A says there may be an intake manifold vacuum leak. Technician B says one or more cylinders may have a compression problem. Who's right? A only. B only. C, both A and B. D, neither A nor B. A vacuum gauge is still a very important tool for diagnosing engine problems. Before we answer this comparative statement, let's review how engine vacuum is produced. As each piston moves downward on its intake stroke with the throttle closed at idle, vacuum is created in the intake manifold. In a cylinder which has low compression due to a leak in the cylinder seal, such as a valve or ring, when the piston moves downward on its intake stroke, air would also enter through the cylinder seal leak. The vacuum created by that cylinder would be less than the vacuum created by the other cylinders, so the vacuum gauge needle would drop regularly each time that cylinder began its intake stroke. Technician A's statement, then, is false. If the engine had an intake manifold vacuum leak, engine vacuum would be low, but the needle would be steady. Technician B's statement is true. If one or more of the cylinders had a leak in the cylinder seal, the vacuum gauge needle would drop on the intake stroke of those cylinders. The correct answer is response B for Technician B only. Vacuum readings at other RPMs and engine operating modes should also be understood as a diagnostic tool. Again, consult your reference material for more information. For this question, refer to the corresponding graphic on your mini-test. What measurement reading is indicated on this micrometer? A, 515 ten-thousandths of an inch. B, 565 thousandths. C, 590 thousandths. D, 615 thousandths of an inch. To properly rebuild an engine, you must be able to use many measuring instruments and gauges. As a general rule, the tools must be capable of reading accurately to 1/1000th of an inch, which is written as .001. Though we will discuss how to read a micrometer in this question, you should be familiar with other measuring instruments such as dial indicators, bore gauges, vernier calipers, and feeler gauges. To use the micrometer, place the object being measured between the anvil and spindle measuring surfaces. Turn the thimble until the spindle contacts the object. The dimension of the object is then found from the micrometer by looking at the graduations on the sleeve and thimble. Each line on the sleeve indicates 25 thousandths of an inch. Every fourth line is numbered, so between each number is 100 thousandths of an inch. Since each revolution of the thimble moves the measuring face one graduation on the sleeve, one revolution of the thimble equals 25 thousandths of an inch travel. The thimble is marked with 25 graduations, each representing 1/1000th of an inch. To obtain the total measurement, start with the highest exposed number on the sleeve, then add .025 for each additional graduation to the right of the number on the sleeve, and finally, add the additional number indicated on the thimble. In this case, the number 5 is exposed on the sleeve as well as 3 additional lines. So far, we have 575 thousandths of an inch. We see an additional 15 thousandths of an inch on the thimble for a total measurement of 590 thousandths of an inch, which would be written .590. So response C is the correct answer to the question. For this question, refer to the corresponding graphic on your mini-test. The gauge setup shown is used to check A, valve guide clearance, B, valve face angle, C, valve face runout, D, valve stem installed height. Engine valves operate in an extremely tolerance-critical world and as such should undergo very close scrutiny during cylinder head overhaul. There are several different gauge setups and measurements necessary to do the job right. For instance, the setup shown checks valve guide clearance as mentioned by response A. Valve guide clearance is the fit of the valve in its guide. This is very important for proper valve seating and oil control. With the valve held off the seat while moving the valve back and forth, the dial indicator will show valve guide wear. Play in excess of as little as 3/1000ths of an inch could mean valve or guide servicing is necessary. The rest of the responses listed in the question are measurements having to do with valves which you should be aware of. Valve face angle, as mentioned in response B, is determined when the valve is cut or ground. Valve face runout, as mentioned in response C, is measured with a special fixture. Runout is measured by rotating the valve in the fixture and watching the indicator. Special fixtures are also available for measuring valve stem straightness. Valve stem installed height is mentioned in response D, and valve spring installed height, which is not mentioned, are two important measurements that must be taken whenever a valve face or valve seat is cut. If a valve face or seat is cut, the valve will move further into the head. The valve stem will now sit higher in the cylinder head. Upon valve train assembly, the valve clearance may not be sufficient and the valve will not close. Also, rocker arm operating angle will be incorrect, causing side loading and premature wear of the valve and the guide. The solution is to trim the required amount of material from the top of the valve stem. Valve spring installed height should also be checked whenever a valve face or seat is cut. The increase in valve stem installed height will increase the valve spring installed height. This will decrease the valve spring tension. Valve springs must be compressed a specified amount to provide proper tension and proper valve function. Valve spring installed height can be checked by measuring the spring's height or length when it's installed on the cylinder head. Spring shims can be used to correct excessive spring height, but don't use shims to compensate for weak springs. Before assembly, the spring should always be checked for squareness and proper tension. When grinding valve face and seat angles, which of the following is true? A, the valve face angle and the valve seat angle should always be identical. B, some engine designs use a 1/2 to 1 degree difference between the valve face and seat angle. C, the valve seat is always ground to a 35-degree angle. Then the face is ground to match. D, none of the above. You may have noticed the use of the weasel word always in two of our responses. In this case, they made our job easier. There are two basic types of fit used when designing cylinder head valve angles: parallel fit and interference fit. Factors such as valve operating temperature, heat transfer, speed, and airflow characteristics must be taken into consideration. Parallel fit means the valve face angle and the valve seat angle are parallel or identical. Interference fit means there's a 1/2 to 1 degree difference between the valve face angle and the valve seat angle. For instance, if the valve face is ground to 45 degrees, the valve seat would be ground to 46 degrees. Because of rapid movement of the valves at high speed and high engine temperatures, which causes the valves to flex and to distort, the interference angle is used quite often. Looking at our responses, we see the correct answer, therefore, is response B. Some engine designs use a 1/2 to 1 degree difference between the valve face and seat angle. Other valve measurements, such as valve margin and seat width, must also be considered when grinding or cutting valves and seats. When measuring and adjusting seat width and location, procedures such as topping or throating may be necessary. Be sure to review these procedures before taking the ASE engine repair test. For this question, refer to the corresponding graphic on your mini-test. The measurement shown is greater than the specification. Technician A says this could be caused from cutting the valve seat and face. Technician B says a valve shim can be added to bring the measurement into specification. Who's right? A only, B only, C, both A and B, D, neither A nor B. The valve spring installed height is being measured in this illustration. When a valve face or its seat is cut, the valve will sit higher in the cylinder head. When the spring is installed in the cylinder head, it will not be compressed as much as it should. This could result in the valves floating at higher RPM. The solution is to place a shim under the valve spring to restore it to the proper installed height. Valve shims come in different sizes and thicknesses to fit many applications. The correct answer is response C, both A and B. Valve overlap indicates the degrees of crankshaft rotation during which A, both valves are open, B, each valve is open, C, both valves are closed, D, none of the above. Valve overlap refers to the number of degrees of crankshaft rotation when both valves are open at the same time. The exhaust valve will remain open a small amount of time after the piston reaches top dead center at the end of the exhaust stroke. Even though the piston starts moving downward on the intake stroke, exhaust will continue to flow out of the cylinder due to its momentum. The intake valve, however, is also starting to open at this time. The fresh air-fuel charge will enter the cylinder due to the momentum of the air-fuel mixture in the intake manifold. This overlap period helps to purge the exhaust gases remaining in the cylinder. Also, at higher engine speeds, when the actual time of the valve events occur very rapidly, volumetric efficiency is increased by packing the maximum amount of fresh charge in the cylinder. Looking at our question, you'll see the correct answer is response A, describing proper valve position during valve overlap. Two technicians are discussing camshaft bearings. Technician A says you can remove camshaft bearings to inspect them, then reinstall them. Technician B says you can measure cam bearing clearance by measuring the camshaft journal with an outside micrometer and the bearing with an inside micrometer, then subtract the difference. Who's right? A only, B only, C, both A and B, D, neither A nor B. When rebuilding an engine or replacing the camshaft, you should always inspect the camshaft bearings. They should be visually inspected for signs of wear. If you're not planning on replacing the bearings, do not remove them from the block or head. Unlike rod and main bearings, camshaft bearings are pressed in place. Once they're removed, they may not be reinstalled. If the bearings show no signs of wear, you can measure the cam bearing clearance by measuring the camshaft journal with an outside micrometer and the cam bearing with an inside micrometer. The cam bearing must be measured while it's in the block. As you can see, only Technician B's statement is true. The correct answer is response B, for B only. For this question, refer to the corresponding graphic on your mini-test. What does the illustration shown indicate? A, excessive clearance at the thrust bearing. B, not enough clearance at number 1 rod bearing. C, excessive clearance at number 3 rod bearing. D, the setup shown is not a valid test. When oil pressure is low but there are no engine noises to indicate the problem area and the oil pump checks out okay, the equipment shown can pinpoint the source of the pressure loss. By connecting pressurized oil to an oil galley, you can see where there is excessive oil flow. Pay close attention to the rod and main bearings, the camshaft bearings, and the lifter bores. If the rocker arm shafts are pressurized, remove the valve covers and view the rocker arm shafts for leakage. This procedure will also help locate a crack in one of the oil galleys in the block. Some bearings will show excessive flow when the oil hole in the crankshaft matches up with the oil hole in the bearing. Because of this, if a rod or main bearing shows excessive flow, the crankshaft should be rotated by hand while performing this procedure. In the illustration shown, number 3 rod bearing has excessive flow, indicating excessive clearance. The correct answer, therefore, is response C, excessive clearance at number 3 rod bearing. For this question, refer to the corresponding graphic on your mini-test. After examining the crankshaft main bearing shown, Technician A states that bearing C controls crankshaft end play. Technician B states that only the lower bearings are shown. Who's right? A only, B only, C, both A and B, D, neither A nor B. While the crankshaft bearings support the crankshaft, bearing C also keeps it from moving end to end. Technician A's statement, therefore, is true. Technician B's statement, however, is false. The bearings shown have a hole drilled in the center. This hole is where pressurized oil is fed to the crankshaft bearings from the oil galleys in the engine block. These bearings must be installed in the upper half of the block, so the holes in the block line up with the holes in the bearings. Therefore, the bearings shown are the upper crankshaft bearings. The correct answer is response A, for A only. For this question, refer to the corresponding graphic on your mini-test. In the illustration shown, a technician is measuring points A and B with a micrometer. What is he measuring? A, rod journal diameter, B, bearing clearance, C, rod end play, D, journal taper. A crankshaft should always be checked before installing new bearings. It should be inspected for roundness, taper, diameter, and finish. The finish is checked with a visual inspection. Look for ridges, grooves, scratches, and so forth. Roundness and diameter are checked by measuring the journal's diameter with a micrometer. Measurements must be taken at the center of the journal in at least 2 locations 90 degrees apart. Any difference between the 2 readings indicates an out-of-round journal. Journal taper is checked by measuring the journal at both ends. Any difference in the 2 readings indicates journal taper. This is what the technician is measuring at points A and B. Therefore, the correct answer is response D, journal taper. For this question, refer to the corresponding graphic on your mini-test. What is the technician measuring in the illustration shown? A, piston to cylinder wall clearance. B, cylinder taper. C, ring end gap. D, none of the above. There are many important measurements that should be made when replacing pistons and rings. Among them are ring groove wear, piston clearance, cylinder taper, and ring end gap. Piston clearance is checked by measuring the piston diameter with an outside micrometer, a caliper. Then measure the cylinder bore with an inside micrometer. Clearance is determined by subtracting the difference between the 2. An alternate way to measure piston clearance is to place the piston and the cylinder bore upside down and use a feeler gauge to measure the clearance. Cylinder taper must also be checked. Cylinder wear varies from top to bottom, with most wear occurring at the top. Cylinder taper may be checked with a cylinder bore gauge, a special tool which uses a dial indicator, or by measuring the bore at the top and the bottom of the cylinder with an inside micrometer and subtracting the difference. Ring groove wear is measured by placing a new ring in the top groove and measuring the remaining clearance in the groove with feeler gauges. The top compression ring groove is the one that usually wears. When piston rings are replaced, each ring must be checked for ring end gap. After placing the ring in the cylinder, square it up by positioning it with an inverted piston. Measure the ring end gap with feeler gauges. Always check the manufacturer's specification for the ring end gap, but a rule of thumb specification is 3 to 4 thousandths of an inch clearance for each inch of cylinder diameter. If the gap is too large, oversized rings may be required. If the gap is too small, file the ends of the ring until the proper clearance is established. Looking at these procedures, you can see that the correct answer is response C, ring end gap. By the way, if ring end gap is being checked in worn cylinders, the measurement should be performed in the lower portion of the cylinder, which tends to show less wear, thus showing less ring end gap. New or newly reconditioned cylinders can be checked at the top or bottom. It's important that the rings have at least the minimum gap. Otherwise, the ring ends may butt, causing ring or cylinder damage. All of the following are true about the use of Plastigauge, except A, the less clearance there is, the more it will crush. B, one size is used for all applications. C, the engine should not be rotated with Plastigauge installed. D, both surfaces should be free of oil and dirt. Plastigauge is a small strip of plastic that is placed between a bearing and the crankshaft to measure its oil clearance. The less clearance there is, the more the plastic is crushed. Before using Plastigauge, both the bearing and the crankshaft must be cleaned of oil and dirt. After placing a piece of Plastigauge across a bearing surface and torquing the cap in place, carefully disassemble the bearing and compare the crushed Plastigauge to a scale on the Plastigauge sleeve. If the Plastigauge does not crush, or if it crushes too much, a different size Plastigauge must be used. There are 3 sizes available. By the way, the engine must not be rotated while the Plastigauge is in place, or a false reading will occur. From this discussion of this except type question, you can see that the false statement, but the correct answer, is response B. A crankshaft is being reconditioned. The rod bearing journals are being cut 10/1000ths. What size rod bearings should a technician use when assembling the engine? A, standard size, B, standard size with a shim, C, 10/1000ths oversized, D, 10/1000ths undersized. If a rod bearing journal is cut 10/1000ths of an inch, it's now undersized. A 10/1000ths undersized bearing should be used. When the bearing is installed in the rod, its inside diameter will be 10/1000ths of an inch smaller than the standard size. This is why it's referred to as undersize. The correct answer is response D. When installing a piston, the notch on the top of the piston should face A, the direction of crankshaft rotation, B, the rear of the engine, C, the front of the engine, D, either B or C. Pistons must be installed properly. On a piston with a dome, it's usually obvious which way to install the piston. However, if the piston has a flat top, it's not as obvious. On most pistons, the wrist pin is offset from the center line. This helps to reduce piston slap noise on a cold engine. The notch on top of a piston should always face the front of the engine when installed. The correct answer is response C, the front of the engine. Two technicians are discussing checking an oil pump. Technician A says you should measure the clearance between the oil pump gears and the housing. Technician B says you should measure the clearance between the oil pump gears and the pump cover. Who's right? A, A only, B, B only, C, both A and B, D, neither A nor B. To check an oil pump, you must measure the clearance between the oil pump gears and the housing, and between the oil pump gears and the cover. All components must be cleaned before any measurements are taken. When measuring the clearance between the gears and the cover, use a straight edge. Always check the manufacturer's specification for the acceptable clearances. However, as a rule of thumb, there should be between 2/1000ths and 5/1000ths of an inch clearance. If the gears, housing, or cover have any ridges or grooves present, they must be replaced. Any measurements that are taken when there are grooves or scoring present will be inaccurate. Incidentally, don't forget to check the pressure regulator valve. Inspect the valve and seat for a good sealing surface and the regulator spring for good tension. As you can see from this discussion, both technician A and B are correct. The correct answer is response C, both A and B. Two technicians are discussing an engine that tends to overheat only when sitting in traffic. Technician A says a faulty coolant fan clutch could be the cause. Technician B says the thermostat could be stuck closed. Who's right? A, A only, B, B only, C, both A and B, D, neither A nor B. Our main clue here is that the engine only overheats when sitting in traffic. When a vehicle is moving, there's plenty of airflow through the radiator to remove heat. When a vehicle is not moving, the radiator fan must draw a sufficient volume of air through the radiator to provide cooling. Many vehicles use a clutch-type coolant fan. These units use a silicone fluid clutch controlled by a bimetallic thermostatic spring. This clutch allows the fan to slip when the engine's cold or when down the road driving supplies enough air to control coolant temperature. This reduces engine drag, increasing fuel mileage when the fan is not needed. As the thermostatic spring heats up from hot air passing through the radiator, the clutch reduces the fan's slippage to increase airflow through the radiator. A defective coolant fan clutch could allow the fan to slip when the engine is hot, allowing the engine to overheat when the vehicle's not moving. Technician A's statement is true. Looking at Technician B's statement, if the thermostat was stuck closed, the engine would overheat all the time. Technician B's statement is therefore false. The correct answer is response A for Technician A only. While we're on the subject of cooling fans, front-wheel drive vehicles with transverse-mounted engines use an electric cooling fan. This fan provides an even greater increase in fuel mileage. In most cases, the fan does not run at all when the vehicle is moving unless the air conditioner's on. When the vehicle is sitting still, the fan will operate when coolant temperature exceeds a specified point. In this program, you've been exposed to many of the measuring and testing aspects of engine repair. In actual day-to-day business, unless you specialize in engine rebuilding, engine repair will take on a whole different focus. You'll see less use of close tolerance measuring techniques and more use of general engine testing and diagnosis. In practice, accurately and profitably diagnosing worn camshafts, ignition problems, warped heads, and slipped timing belts is the major part of the job. So, to be properly prepared to take the ASE engine repair test, you'll have to master the material covered in this video, as well as the material found in the task sheets.